Hello dear learners. In this lecture, we will discuss more aspects about the sun and the interplanetary space. Right. So, in the last class, we have seen what is the fundamental mode of energy transport from the core towards the surface. There are two different modes, one radiative transfer and then transfer by convection. Okay. Now, like I said in the last class, apart from all the other physical properties of the sun as a star, as a ball of plasma, rotates around itself, but it rotates faster near the equator and slower near the poles. So, as a result of which, as a result of this differential rotation, all the solar prominences are created, or they uh, they evolve as a result of this solar rotation, or the difference in the speed over which the different latitudes complete this 2 pi angular displacement. Okay. Now, what are the solar prominences? Like I said, solar prominences are many actually. There are like visible coronal mass ejections and solar flares, and then in addition to this, you can also have this coronal loops. All these different phenomena, X radiation, X-ray burst, or different energy outbursts from the sun, most of them are associated with the differential rotation, right? Now, when you talk about energy that is transmitted or energy that is coming out from the sun, we are looking at an object which is heated to 5800 Kelvin. Okay, so as simple as that. For all practical purposes, we are looking at an object which is at 5800 Kelvin. Okay, and this object is radiating electromagnetic radiation. So, from the thermodynamics, we know very well that any object at any temperature will radiate energy. Right? So, 5800 Kelvin. So, how much energy are we getting from the sun? So, this energy is distributed, let us say, in from 0.1 to approximately 10 to the power of 6 nanometers, which is centered in the visible. So, we have already seen what is visible, how much energy is 43% of the energy is contained in the is bundled into visible spectrum, and the remaining energy in the ultraviolet, infrared, far infrared, basically short and long wave radiation. Right? Now, how much energy are we talking about? We have to convert this into joule, or let us say into the units of power. So, now for that we can imagine a disk to be kept at 1 astronomical unit distance from the sun, and since the diameter of this disk is going to be the diameter of the earth, which is 12,800 kilometers. Now, this energy is falling onto the disk. You can do a simple calculation by using the Stephens-Boltzmann's law. You will realize that how much energy is actually falling on this disk. So, energy from the sun passes through an imaginary disk. Then if you do that calculation, you will realize that approximately 1370 joules per second per meter square is the energy that we are receiving from the sun. Okay. Or the power is 1370 watt per meter square. Okay. So, this energy is projected onto the sun, this energy, edit here, this energy is projected onto the earth. And the way it works is that because you have a curved surface, the energy will be deposited unequally over the equator in comparison to the poles. Imagine this, you have a curved surface and you have the energy, which is, let us say you take this disk right now. Okay. So, this energy is transported. So, you take 1 unit surface area on this disk. Okay. This is 1 unit surface area of the disk. So, whatever the energy that is coming here, okay, 1370, if it is projected onto a unit surface area, then you would expect that every point on this earth will get equal energy input. But what happens is, Because you are projecting it onto a curved surface, this area, if it is projected onto the curved surface, will occupy an area like this. Okay. If you go towards the poles, the area will be larger, the projection. Now, this is the reason why the equator is heated more in comparison to the poles. This essentially drives the circulation. That is a different topic, but for to simplify this discussion, what we can simply say is that to simplify this discussion, we can say that 1370 watt per meter square is the amount of power that we are getting from the sun. Now, if you put this in comparison to the rotation of the earth around the sun, you can easily realize the seasons. So, now 23.5 degrees is the axial tilt. Now, you see this during this period of time, the polar region. Okay. So, this is completely turned away from the sun. That is why we get no direct sunlight during this period of time, or we can say that this is northern hemispheric winter. And exactly opposite happens in after 6 months, where this region is completely brought into the illumination, and the exactly opposite happens in the southern hemispheric winter. This is northern hemispheric summer, and this is southern hemispheric winter. This is the seasons. The seasons occur because of the tilt of the Earth's axis keeps a constant orientation as the Earth revolves around the sun. Constant orientation. Okay, so the summer in the northern hemisphere means winter in the southern hemisphere. So, we are experiencing summer in the let us say in June onwards, May, June, July. The other hemisphere, the southern hemisphere, is experiencing winter. Okay, right. Now, let us briefly look at some other aspects related to the various regions of the sun. So, we can start from the core radiative zone, radiation zone, convection zone, solar wind, corona, transition zone, chromosphere, etc. The core is, of course, the dimensions are clear. The radiative zone, energy transfer is going on. Energy transfer within the radiative zone is happening by the means of electromagnetic radiation, because all the atoms and molecules are completely stripped of their electrons. As a result, it is in a highly completely ionized state, as a result of which energy can neither be absorbed by the atoms and molecules, because all the electronic states are not there. That is why the entire medium becomes transparent or becomes equal to vacuum, but there will be collisions. So, no photon originating from the core will ever reach the surface, because of collisions, because of scattering and all that. Energy, of course, is being transported by the means of radiation, but still it will not reach out. Okay, it will always be, this is a continuous process, of course. And then you have the convection zone, which means convection is material when it comes close to a heat source gets heated up, its density will decrease, it will move upwards, and this void in the bottom created by the vertical movement of the air is filled by cold air, and as a result you get to see a convection cell. So, this is a method by which energy is being transported from the lower altitudes towards the higher altitudes. So, this convection cell is making the energy move from one place to another place. And then above the convective zone, of course, it is the photosphere, right. So, this is the interior. The surface is the photosphere, and atmosphere is starting from the surface. So, atmosphere has all these parts: chromosphere, transition zone, corona, and the solar wind. Solar wind is the constant stream of particles, highly energetic particles, which are leaving the sun and moving towards the outer space, moving towards the edges of the solar system. So, solar wind is something that reaches the earth, whereas all these are associated with the sun. Okay. So, solar interior, we have to understand. I have said so many things about the solar interior. So, how do we know what is inside the sun, and how do we how people came up with these numbers? Okay, so you have to think about these things, then you will understand. Okay, now the chemical composition is hydrogen, helium, mainly dominating, oxygen, carbon, iron, neon, nitrogen, silicon, magnesium, sulfur, and nearly many other naturally occurring elements are present in a reasonable concentration on the sun. Because when you put to perspective, all these, although very small fractions, are still much larger than the mass of the earth itself, right? So we cannot neglect them, right? So then we talk about the differential rotation, a key concept in understanding solar prominences. So, differential rotation means the latitude 0 or the equator rotates around itself in 25 days. So, it's very fast in comparison to the poles. Why it is rotating like that, or why the speed is not the same and everything, they are completely beyond the scope of this particular discussion right now. But if you are looking at the for understanding the solar prominences, it is at this point of time, it is enough to know that sun rotates around itself at different speeds at different latitudes, 34.4 days. So you can remember it should be like 25 to 35 days, a difference of 10 days, let's say. So at solar equator, it is much faster, 26.8 days, and maybe it's many places this number of days are reflected differently. So you can remember something like 26 or 27 days and 32 days at the poles. Okay. Now, as a result, what happens is going to be very interesting because of this differential rotation. What changes? Okay, what is affected inside the sun, and how this effect will lead to the formation of solar prominences will be very interesting. Now, more importantly, the interior properties. Sun is a ball of plasma. The density of the core is 20 times the density of iron. Okay, so it's not a gas. It is highly dense material where the fusion is going on. Again, this density, how do we know? No instrument has ever been near the proximity of the sun, let alone going inside the sun. How do we know that the density of the sun is of this order, 20 times the density of iron? Whereas the density of the surface is 10,000 times less dense than air. Air at STP, you see, 1.225 kg per meter cube. The density, so this is 1 meter cube of air will have 1.225 kgs of a gas of nitrogen and oxygen with 78 and 21% concentration. Now, if you take that, the surface of the sun is going to be 10,000 times less dense, right? So, I mean, the number of atoms and molecules that you can find within 1 unit volume will be very, very less in comparison to what you see on the earth. So, there is a drastic drop of density from the core towards the surface, isn't it? Now, put together, you take an average of densities from this core towards the surface. Average density is roughly of the order of Jupiter, right? So, if conditions permit, okay. Now, the average density is roughly of the order of Jupiter. And surface gravity, we know that 9.8 meters per second square that we know. For the case of Earth, seems to be very large for the case of Sun, which is 274 meters per second square. So, any object falling towards the Sun, its velocity will increase by a magnitude of 270 meters per second for every second. So, 0, 274, and then 274 plus 274. So, that is how fast an object will be pulled towards the sun when it reaches a particular limit. Okay. and this surface gravity translates to an escape velocity of 618 kilometers per second, which is immense. 618 kilometers per second is something that we will not be able to achieve that easily. Okay, and then the core temperature we already know, the surface temperature also we already saw that. So this is how the density changes from the center. It is very, very high to very, very low near the surface on either sides. Okay, and then the temperature is 15.6 or 16 million Kelvin here, and it reaches, by the time you reach the surface, it reaches 5800 Kelvin. Okay, now let us look at the various zones of the sun inside first, and then we will talk about the atmosphere as well. So the radiation zone is, this region is transparent to light. What does it mean? Something is transparent. A medium becomes transparent when the medium is not able to absorb any of the incident radiation or the radiation that is passing through it. That's the basic definition of transparency. Okay. Now, something is opaque means radiation or the energy or the electromagnetic wave or the electromagnetic radiation is absorbed. Some part is absorbed. So whatever you get is not equal to 1. So transmission plus reflection equal to 1, right? So this radiation zone is transparent to light. So if you remember in the last class, we have seen that visible radiation is the most form of energy output from the sun, approximately 50%. But interestingly, none of this radiation is utilized in the atmosphere or is absorbed in the atmosphere. All of the visible radiation passes through the atmosphere just like that, which means the atmosphere is transparent for visible radiation. Similarly, the entire radiative zone, so several of the order of 400,000 kilometers of radius, the radiation zone, that much distance, it is entirely transparent. So light will not be absorbed. Of course, there will be scattering because it is not vacuum. It is not vacuum. You cannot expect vacuum to be sitting in the middle of the star. So because of the immense amount of energy, 15.6 million Kelvin, that is being created there, all the matter is existing in the highest possible ionized states. Okay, so it cannot absorb energy. Okay, so at the temperatures near the core, all the atoms are ionized. They are existing in highest possible ionized states. So if you think of any element, you see how many number of electrons are present, and then you remove all that, then that becomes the highest possible ionized state of that atom. So electrons are floating freely from the nuclei. All electrons are stripped off from the nuclei, and if the light wave hits the atom, there is no electron. The electronic excited states are not present. As a result, there is no electron to absorb it. Okay, so as a result, this interaction of light and atom, which is essential for the absorption, will not happen. So that's why there is transparency. That's why the entire radiation zone is transparent to light. But of course, there are collisions, there will be scattering and all that. That's a different story. That's probably why we never get to see the light which is from the core on the surface. Okay, so light, this interaction, because of the lack of this interaction, energy is passed from the core through this region and towards the surface by radiation. Not entirely, but up to the bottom of the convection zone. Okay, then comes the convection zone, which is basically sitting just above the radiation zone, which is approximately a quarter in size in comparison to the radiation zone. So this region is totally opaque to the light. This is very important. That means light will not cross this region. Light only will heat up the bottom of the convection zone, allowing the matter that is present to rise in altitude, to rise and create a convection cell. Why? Which is, the convection zone is closer to the surface, the temperature is much cooler, and as a result, because energy is being transported directly, right? So it will, as you move away from the core, there is some loss, and the amount of energy available per packet will not be that much to ionize everything. So atoms and molecules are not completely ionized. They are not completely ionized. So there are electrons around the nuclei can now absorb the light from the below. So essentially, no light from the core ever reaches the surface. This is a very important statement. No light from the core ever reaches the surface. It only the bottom, the topmost height they reach, the light reaches, is the bottom of the convection zone. Okay. Well, so where does the light go? Energy instead makes it to the surface by convection. So like I said, the convection pattern. So what is convection? Convection is simply hot material rises, cool material sinks, forming a cell which is basically doing the energy transport. Okay, so this is how it looks like. So radiation is heating up the bottommost part of the convection zone, and as a result, these convection cells are forming, which are which is like a cascade. This convection cell deposits this energy. By the time they lose the energy, they deposit at the bottom of the next layer of convection cells, and as a result, energy thus makes it outwards towards the surface. Now you see the convection cells, the progressively smaller convection cells carry the energy towards the surface. The size of the cell, if you see this figure carefully, the size of this cell is becoming progressively smaller as you travel away from the core or from the center. Why? Because at the bottom of the convection cell, the energy input is so high. So as a result, more energy input, the size of the convection cell will be larger because you have given a lot of energy to the fluid and it can rise to a larger extent. And it will rise, of course. Nothing is conserved. The same amount of energy can never be transported to the other side. There is a loss. So as a result, the immediate convection cell layer that is sitting above will receive a fraction of the energy that has been given to the first cell of convection layer, first layer of convection cells. And it goes on like that. As a result, the sizes of the convection cells become increasingly smaller as you move away from the center. Right. Ultimately, whatever that happens inside, like I've been saying, whatever that happens inside from the core towards the surface, the outermost layer is heated to 5800 Kelvin, which you call as the temperature of the photosphere. Okay, so this figure shows these small distinguishable regions that I'm just drawing here are basically the convection cells that I'm talking about. So if you look in an image, you will see that the matter is rising in this convection cell and then falling. Okay. So we also talk about what is called as solar granulation, photograph of the granulated solar photos. So if you look with a high resolution instrument, you will realize that the solar sun, edit here. If you look with a high resolution instrument, you will see that the surface of the sun is not uniform. It will appear as if it is a collection of small granules. So this is called as solar granulation. What are these small granules? These are the convection cells which are carrying the energy from the radiation zone towards the outer surface. Now, the typical solar granules are comparable in size to the Earth's continents. The bright portions of this image are the regions where hot material is upwelling from below. The dark regions correspond to cooler gas that is sinking back into the interior. Okay. Right. Now, these images, many of much higher resolution images are also available on the internet. You please try to see those images and develop a feeling for all the physical processes that I have covered in this lecture. We will continue this discussion with more interesting aspects about the sun in the next lecture.